The period t of the motion is the time taken for one revolution to occur. The particle travels a distance equal to the circumference, which is given as 2 pi r. So we can write that speed is equal to distance over time, which gives us v equals 2 pi r over t. Now solving for t, we get t equals 2 pi r over v. Now I want us to recall that we've already written v as omega r, meaning v, which is the linear speed, is equal to the angular velocity times the radius. So we can substitute this into our expression for t, and we get t equals 2 pi r over omega r. Now the r's cancel out, so what we are left with is t equals 2 pi over omega. And this is the expression for the period of the oscillation in circular motion. Let's apply the knowledge we have so far to some cases where we have circular motion. The first instance is that of a conical pendulum. Consider a small object of mass m tied to a string of length L fixed at a point O and then whirled round in a horizontal circle of radius r, with the fixed point O directly above the center of the circle as shown. We assume that the circular speed of the object is constant and the string turns at a constant angle theta to the vertical. This arrangement is called the conical pendulum. The tension in the string has two components, ft cos theta and ft sin theta. Since the object moves in a horizontal circular path, the horizontal component ft sin theta of the tension ft in the string provides the centripetal acceleration along the radius of the horizontal circular path, so that ft sin theta equals mv squared over r. Let's call this our first equation. The weight of the particle, mg, must be equal to the vertical component of the tension, ft cos theta, since the object does not move in a vertical direction. We can therefore write ft cos theta equals mg. And let's call this equation 2. Dividing our equation 2 by equation 1, we get tan theta equals v squared over rg, which can be written as v equals root rg tan theta. Now recall our equation for the period of uniform circular motion, where we said t equals 2 pi r over v. Substituting our expression for v into this, we get t equals 2 pi r over root rg tan theta. Simplifying this, we get from our diagram, we can see that our radius r is equal to L sin theta, where L is the length of the conical pendulum. This means that we can write the period as t equals 2 pi root L sin theta over g tan theta, which simplifies to t equals 2 pi root L cos theta over g. And this is our formula for the period of a conical pendulum in terms of the length L of the pendulum, its angle to the vertical, theta, and the acceleration due to gravity, g. Another example of circular dynamics occurs when an automobile rounds a curve. For the car to move in that curve, it must have a force exerted on it towards the center of the curve to serve as its centripetal force. On a flat road, this force is supplied by friction between the tires and the pavement. This friction is static in nature because there is no relative motion between the tires and pavement in the direction pointing towards the center of the curve. But what happens when the static friction is not sufficient to provide the centripetal force, as in the case of a slippery road or high speed, or a tight curve where the radius of the curve is very small? Well, when this happens, the car will skid or slide out of the circular path into a more nearly straight path. Banking is a technique in road construction that involves tilting of the road surface at an angle above the horizontal, inward to the center of the road. The banking of curves can reduce the chance of skidding, and the normal force exerted by a banked road acting perpendicular to the road will have a component towards the center of the circle, thus reducing the reliance on friction. Now let's analyze this effect of banking and see exactly how it works. As you can see, I've illustrated the forces acting on the vehicle moving along a banked road in a circular path. We have the normal reaction exerted by the road on the car, the force due to friction pointing in a direction parallel to the surface of the road, and the weight of the vehicle. Now, if we resolve these forces into horizontal and vertical components, what we get is something that looks like this. Now, the total horizontal force available to provide centripetal acceleration is given by F cos theta plus N sin theta equals mv squared over r. Let's call this our equation 1. We can see that the centripetal force now relies not only on friction, but also on the normal force exerted by the road on the car. Now, since the car does not move in vertical direction, we can also write N cos theta minus F sin theta minus mg equals 0. And we call this our equation 2. Now, generally, we all know that friction in many cases is undesirable. For example, in this case, it can lead to wear and tear of our car's tires. So if we take a closer look at our first equation, we see that as the banking angle increases, the friction component reduces because the cosine function reduces as theta increases, and vice versa for the normal reaction component. This means that increasing the banking angle initially reduces the required frictional force. If we continue increasing the angle of banking, we get to an angle where there is no friction required. This angle is called the optimum angle of banking, theta naught. To get an optimum angle of banking, we set F, which is our frictional force, to 0 in both equations and solve for theta. Doing this, we get N sin theta equals mv squared over r, and let's call this equation 3. And doing this in the second equation, we get N cos theta equals mg, and let's call this our equation 4. Now, if we divide our equation 3 by equation 4, we get where theta naught is our optimum angle of banking. We can rewrite this equation as theta equals the tan inverse of v squared over rg.